A child in a boat throws a 5.4 kilogram package out horizontally with a speed of 10 meters per second. Calculate the velocity of the boat immediately after, assuming it was initially at rest. The mass of the child is 26 kilograms and the boat is 55 kilograms. You know this is a momentum problem, and for momentum problems, you got to draw a picture of the beginning of the problem and the end of the problem. So the beginning, you got a kid just hanging out here on the boat. The total mass of all three of them together is 86.4 kilograms. At the end, though, he chucks the package to the right at 10 meters per second, and we want to know how fast all this stuff is going over here. Now, before we even solve it, just looking at the problem, you can probably guess, you know from Newton's third law, that if you chuck this thing to the right, if you push it to the right, it pushes you to the left. But check it out. The mass of the kid in the boat is a lot larger than the mass of this thing. So you know that this is going to be a much smaller velocity than 10 before you even solve it. But let's add up the momentums for each situation. So adding up the momentum in both cases, at the top you've got the total momentum is just, you add up the mv for all the objects. Well, none of them are moving, which means you have a total momentum of 0. So at the end of the problem, you also must have a total momentum of 0 when you add up the mv for every object. So if we add up the mv for this object, we get 5.4 times 10, and for that object, it's 81 times the unknown velocity. So since we don't know what it is, we just write it as a v. So simplifying a little bit, we've got 0 equals 54 plus 81 v, trying to find the velocity of the kid and the boat at the end. And we just want to get this v by itself. So we subtract out the 54, and then we divide by 81 to get the v, which we get minus 0.67 meters per second. The minus here simply represents that he's moving to the left, which we already really knew. And it makes sense. If you throw something small at a velocity of 10, it makes sense that if you take something about 10 times bigger, that it would get a velocity that's only about 1/10 as great. So all is right in the world. See you on the next one. A 9,500 kilogram boxcar traveling at 16 meters per second strikes a second car. The two stick together and move off with a speed of 6 meters per second. What was the mass of the second car? As with all momentum problems, let's draw it before we begin. So here's our problem drawn out. At the beginning, we got the green cart moving to the right and the orange one's chilling. And then the green one smashes into the orange one, and a bunch of speed actually ends up being lost. So you know that kinetic energy is not conserved in this case, but momentum must be conserved. So to calculate the momentum in this problem, we just use momentum equals, you add up the mv for every single object. Well, in this case, you know the momentum of the orange one's going to be 0 because it's not moving. So the entire momentum is contained in the green cart, and we get... So adding up the mass times velocity for every object, we get 9,500 times 16, which gives us quite a bit of momentum, 152,000. But not a big deal. We can still work it. Don't let the big numbers scare you. That means down here at the bottom, the total momentum has to be the same. It's 152,000. And that's equal to adding up the mass times velocity for every single object. So writing it out, we've got the total momentum of the green cart, which is its mass times its velocity, plus the total momentum of the orange cart, its mass times 6, had better equal 152,000. And from here, it's pretty simple to solve for what m is. So working this out, we just want to get the m by itself. So we subtract out this part. We subtract the 57,000. And then we just end up dividing this chunk of stuff by 6 to get m by itself. We get about 16,000. So turns out the orange cart was quite a bit larger than the green one. So I didn't quite draw it to scale at the beginning. I should have had a chunkier orange cart. But sometimes it's hard to tell before you solve the problem, but now we know that this is in fact the larger cart, which kind of makes sense. This thing was really trucking at the beginning of the problem, but at the end, it lost more than half of its velocity, so it makes sense that this one was quite a bit chunkier.